All right, welcome back to the hottest seminar talks. Today, we are very happy to have our very own Dan Christensen, who's going to tell us about sphere bundles and their invariants.
Great. Thank you for the introduction, Emily. And thanks also for encouraging me to give the talk repeatedly. I appreciate that. So I'm going to talk about work that's covered in two papers. One paper is by this group of 4 authors, Buchholz, myself, Flatten, and Reika, and it's available on the archive. And there's a newer paper that is not quite ready for the archive, but we were hoping to get it done before this talk, but maybe another month or so till we get some of the things polished there. So, and it's a slightly different group of authors. It's got David Jas-Myers in place of Ural Flatten. So there'll be a part this part about central types will involve the first paper, and the later parts will involve the second paper. I'll also mention that I do have the chat open, so I just noticed that Emily posted in the chat. I may not always notice, but feel free to ask questions that way, or even better, just unmute your mic and ask me. I don't mind at all. Okay, so I'm going to start with just talking about bundles, what the concept means in homotopy type theory. This is just review. Then it's going to seem like I'm going in a different direction when I talk about these central types, but you'll see that some of the same characters show up there. And then I'll come back to talking about bundles when I talk about the Euler class and the Thom class, and I finally will get to the Harry-Ball theorem at the end. Okay, so first, just a bit of motivation for what we're going to be talking about. So in classical homotopy theory, vector bundles play a very important role. They arise, for example, as tangent bundles to manifolds. Projective spaces have vector bundles over them, the canonical bundles. When you embed one manifold into another, there's a normal bundle. And in general, when you embed a manifold into Euclidean space, the normal bundles there tell you a lot about the manifold. And in other situations in geometry, you often have various bundles of geometric structure. Now, in homotopy type theory, a vector space is contractible. So if I'm just using plain homotopy type theory, which is what I am doing, we don't have a good theory of vector bundles if we try to just work directly with the idea of a vector space. But what we can do is instead look at the associated sphere bundle of a vector bundle. So there's 2 ways you could think about this. One is that you could take it to be the unit vectors in the vector bundle, or alternatively, you could just take it to be the non-zero vectors. Homotopically, that's also a sphere. So we're going to be studying sphere bundles as a replacement for vector bundles. The theories are not equivalent, but we'll see that much of the information in a vector bundle, many of the invariants factor through the sphere bundle construction.
Sorry, Dan, so I was thinking of a third choice where you do some sort of one-point compactification, and I'm wondering if you could discuss, I mean, is that an interesting variant or?
Yes, it is actually. So I'm going to be talking about Thom spaces in the second half, and that's roughly speaking a one-point compactification. It's a one-point compactification of the total space. So that will also be something that comes up. Yeah, thank you. Okay, so conventions very briefly. I'm following book hot, usually using book notation. So I'll be using some pushouts, some truncations, and I'll be using a univalent universe or 2. And I'll be using univalence very implicitly. So I'll translate between equivalences and equalities of types transparently. And I'll also be using function extensionality to translate between homotopies and equalities of functions. Okay, so let's get started by talking about bundles. So we're going to talk about bundles with a certain fiber. So T will be the type of the fiber. And then a T bundle, one way to talk about it, when we have a certain base B, is to take it to be a family of types. So U is my universe. And I'll require that pointwise, the values of this family are equivalent to T, but only merely. So this is the propositional truncation for every point in the base. So a family of types, pointwise, merely equivalent to a fixed type. And we can bundle up that data as a map from B into B ot t, where B ot t has as its first component a type. That's the value of this function p. And then the second component is the proof that that type is merely equivalent to t. So this type of pairs B ot t is the natural way to describe bundles with a given fiber. Just as an example, T could be bool, a two-element set. So then B ot T would be the type of all two-element sets, which turns out to be RP infinity or K Z mod 2, 1. But we'll be studying this for a variety of different T. So in general, there's a correspondence between maps into the universe and functions into B. And that gets refined when we put this constraint on the fiber values. So maps from B into B ot T will correspond to a domain E, a function from E to B, and the condition that for every element of B, the fiber of F over that point is merely equivalent to T. So in this sense, we'll say that B ot T classifies maps whose fibers are merely equivalent to T. And in fact, you can see that classification as a pullback. I've written it down here in the case where we start with a type family. Then we can form the total space of that type family. And here, P of B, strictly speaking, is a pair of a type and a proof that it's merely equivalent to T. But when I write it in this context, I mean just the type, the first component of that pair. So this is the total space of the type family with its first projection. And there's also a corresponding total space for the canonical type family over B ot T. So for every element of B ot T, I can take the type component and take the sigma type of all of those. There's my function P. And this function is easy to describe. If I give you a little b and a little x in P of B, what I'm going to send it to is the type P of little b, and then my little x, which is in P of B. And this also works if I put a general map of this form in this spot. There's, again, going to be a classifying map by going across this equivalence, and we'll get a pullback square. So we call this the universal T bundle. And if I took T to be bool, this would be contractible, because if I have a type that's merely equivalent to bool and I choose a point in it, then I get I can deduce an equivalence to bool from that. But in general, this won't always be contractible. It's some domain of the universal T bundle. And maybe I should just say what this equivalence is. If I give you a type family, then E is the sigma type like we formed here. F is the first projection like we formed here. And then you have this proof that all the fibers are T because of what you started with. And in the other direction, if I start with the data here, I can take that F and look at the function fib sub F, which sends B to the fiber over B. That'll be a type family, and with this data, I have the proof I need for the second component. So that's how I go back and forth here. Okay, but we're going to be focused on a slightly more refined notion of bundle. So the first line here is just reminding you of what we did on the previous slide. But we're going to talk about oriented bundles. So instead of mapping into this B ot T, we're going to map into something I'll call B ot 1 of T. And at the bottom of the slide, I'll explain why we choose 1 as the subscript here. So B ot 1 of T consists of a type, but instead of just merely having an equivalence to T, I have a homotopy class of equivalences. So I've changed the -1 truncation to a set truncation here. So that is not just remembering that there is an equivalence, but it's saying I know it up to homotopy. Okay. So a little bit more information is being stored here. So just as an example, if X is a mere sphere, then if I -1 truncate here, this type is contractible. But if I set truncate, this type has 2 elements. So I'm remembering an orientation of the sphere in that case. And if I studied this one in the case of Boole, remember B-ought Boole was RP infinity. B-ought 1 of Boole turns out to be contractible because self-equivalences of Boole form a set. So the set truncation here doesn't do anything. I can remove it, and then I can change the equivalence to a path, and then I have a singleton here, which is contractible. So just to explain the notation, so we have these forgetful maps. If I have a type that is oriented by T, so it has this set truncated equivalence, I can -1 truncate that to get a mere equivalence, or I can completely forget the equivalence and get a type. So the first one here, B-ought T, it's the component of the universe containing T, which you could also call the zero connected cover of this pointed type. So this is always a connected type, and it's the sort of the universal pointed map from a connected type to the universe pointed at T. And the second one, the B-ought 1, I can rewrite the set truncation as an equality between 1 truncations of X and T. So that's one of the things you can prove using univalence about truncations. So that's telling us that this B-ought 1 of T is actually the fiber of the 1 truncation map at the image of T. And that fiber is what we call the 1 connected cover of this pointed type. And it is 1 connected, simply connected, and it's the universal simply connected type mapping to U. So it's also called the universal cover. And that's where the 1 comes from in the notation, because it's a 1 connected cover. Okay, so these oriented bundles are going to play a big role, but this is where I take a little bit of a detour, and I start talking about that first paper I mentioned. And at first glance, it might be weird that I'm doing things in this order, but you'll see why in a moment. Okay, and by the way, Jarl Flatten gave a hottest talk a couple of years ago talking about some parts of this paper that I won't get to in this talk. So if you're interested in it, please see that talk. All right, so we've talked about the component of a type. So let me introduce the notation for it. So if X is a type and little x is an element, then I write this notation with parentheses around X to mean the component of capital X containing little x. So it's the set of all y in X, where y is merely equal to little x. And then here's the condition I'm going to put on a type, which seems strange, and we'll see some things it's equivalent to and understand why it's a powerful assumption in a moment. So I just start with a pointed type. I can always form the following map. So I take all the self-maps of T, unpointed self-maps, and I take those in the component of the identity map. So in other words, I take the self-maps that are homotopic to the identity map. Then I can evaluate such a self-map at the base point of T to get a point of T. So I send F to F evaluated at a point. If that map's an equivalence, I'll say T is central. It seems mysterious, but when we were trying to prove various things about Eilenberg-Mac Lane spaces, we kept on realizing that this equivalence for Eilenberg-Mac Lane spaces is what we were using. And so we were able to abstract those arguments to any type that satisfies this. And I'll say a little bit on this slide about some examples, but then I'll say more 3 or 4 slides from now. So before I can get to some examples, here's, well, first here's a fact, and then I have a proposition. So first, since T will be equivalent to a component, it will be always connected. And this type on the left is an H-space because I can compose self-maps of T. And the identity map is a 2-sided identity for that. So an H-space is a type with a binary operation and with an element that is a 2-sided identity for that operation. So this type is an H-space, and if T is equivalent to it, the H-space structure will transfer across that. So every central type is a connected H-space, just fairly immediately from the definition. And then the proposition gives these 4 characterizations of central types. So first one is centrality, and then the next three all have that T is a connected H-space, and then a different extra condition. So we can take that the pointed self-maps form a set, or the pointed maps to the loop space is contractible, or I can adjoint the loops to the suspension and get that that's contractible. Those are all equivalent. And I can give you a little sketch about why that's true. So if T is central, then this map is an equivalence, which tells us that its fiber is contractible. And the fiber of this will be the pointed self-maps that are homotopic to the identity as unpointed maps. But because T is an H-space, the trick of Evan Cavallo will tell us that, in fact, this is equivalent to the pointed self-maps that are pointed homotopic to the identity map. And so that type will be contractible. And that type is one component of this type. But again, since T will be an H-space, this mapping type will be an H-space, and all of its components will be equivalent. So if one of them's contractible, they all are, which means that this is a set. I know that was maybe a lot to absorb, but I just wanted to give a sort of the rough idea. And the argument backwards is just follows that argument backwards. If this is a set, then each of the components is contractible. In particular, the fiber of this over the base point is contractible. And that gives us that 1 and 2 are equivalent. The rest are even easier because this is the loop space of this. The loop space of a pointed mapping type is the pointing mapping type into the loop space. So this being a set will tell us that its loop space is contractible. And here we just have the suspension loops adjunction, giving it these types are equivalent. So this isn't a very hard proposition, but it shows that there's some very concrete things you can check to see if a type is central. And then we can use those for a couple of examples. So first of all, every Eilenberg-Mac Lane space for an abelian group at a positive natural number n is central. That's easiest to see from this condition. These are connected H-spaces because they're loop spaces. And the pointed self-maps of a KGN are the group homomorphisms from G to G, which form a set. So we get condition 2 holding. The problem if G is not abelian is that a KG1 for G non-abelian isn't an H-space. So that's the part that fails there. The 3-sphere is a connected H-space, but it's not central because pi4 of S3 is Z mod 2. So that means this type of pointed maps, in this case, would have 2 components. It wouldn't be contractible. Okay. So I'll tell you a few more examples in a bit, but those are the ones I wanted to talk about at this point. All right. Let's go on. So here I'll start to tell you some of the powerful things that are true when you know that a type's central. So here's the definition. The first thing is that if T is central, this thing we already defined, B.1 of T, turns out to be a delooping of T. Okay. And this is where you see why I first talked about oriented bundles, and then I did this detour into central types, because B.1 of T makes an appearance here. So when I say it's a delooping, what I mean is that when I loop it, I'm going to get T. And so let's just check this. So if I want to loop B.1 of T, by definition, that's the paths between the base point and itself. And the base point is T with the identity equivalence. So I get this equality. And now I have a path between pairs. So that's given by a path between the first components, which I'll write as an equivalence using univalence. And then I have to transport the second component to be equal to the second component. And that transport is given by composition of homotopy classes. So this is a truncated composition. So then you can see from this that the homotopy class of E must be equal to the identity, which means that I'm looking at self-maps that are homotopic to the identity. And here, it doesn't matter whether I put maps or equivalences, because if you're homotopic to the identity, you're automatically an equivalence. But then by centrality, that mapping type is equivalent to T. So you see that centrality is exactly what we need at this point in the argument, which is why it's the definition. And I should say that David Varn has a more general delooping result than this under weaker assumptions. Okay, in fact, you can get a unique delooping. You can show that any delooping is equivalent to this one, and that will be useful as well. But the next thing, which has got a more complicated argument, so I won't sketch it, is again, if T is central, then pointed self-maps of T also deloop, and they deloop uniquely. So on the left, I've got the deloopings of T, and given a pointed self-map here, I can apply the loops functor to get a pointed self-map of T, and I'm saying that that's an equivalence, so that every pointed self-map has a unique delooping. So there, the construction that takes the pointed self-map and gives the delooping is a little bit involved. I can't really write it down concisely. Okay, so those are two important things, and we're going to use them in a moment. And then there's one more thing that happens for this B-1 of T whenever T is central. You get that it's always an H-space. So in order to do that, we first need this proposition. So suppose I have two types X and Y that are T-oriented. So omega and gamma are these truncated equivalences to T. Then the type of paths between them inside B-1 of T, that type itself is T-oriented. So in other words, I need to construct a set truncated equivalence from the path type to T. But since my goal is a set, I can remove the set truncations on the equivalences I have between X and T and Y and T. And I can use univalence to make those paths and then do path induction so that I can assume I'm at the base point here, that X is T and omega is the identity equivalence, and same for Y. So in other words, I need to show that the loop space of B-1 of T is equivalent to T, which is what I did on the previous slide. I can do it without the zero truncation even once I've removed the truncations here. Okay, so that gives me a way to orient this type. And I can use that to give a binary operation on B-1 of T. It's not exactly this type. So given two oriented types, I'm going to write tensor for this binary operation, which is essentially this path type, except that I'm going to change the orientation of X slightly. So I take this equality type, I use the orientation from the proposition, so I get an element of B-1 of T. And I change the orientation on X by taking the orientation I have, and I post-compose with the self-equivalence of T, which is given by inversion. So remember, T is a connected H-space, and in a connected H-space, every element has an inverse. So the map that sends an element to its inverse is an equivalence, and I post-compose this homotopy class with homotopy class of that equivalence. So that's the star operation. Okay. So then the theorem is that that operation does make B-1T into an H-space, where the base point, which is T with the trivial orientation, is the identity. In fact, it's commutative. And then this is going to give us, this combined with what was on the last slide is going to give us something a little bit surprising. So if T is central, then B-1 of T is again central. That means you can iterate the process. B-1 of T is a central type, so it has a unique delooping, B-1 of B-1 of T. And you can keep iterating that. So it follows that every central type is an infinite loop space in a unique way. So the proof, B-1 of T, it's one connected. It's the one connected cover. So in particular, it's connected. And we just showed it's an H space. So by the proposition 2 slides back, we need to show that the pointed self-maps of B out 1 of T form a set. But the unique delooping of maps tells us that that mapping type is equivalent to this mapping type, and this one is a set, again, by that proposition characterizing central types, used in the other direction there. Okay, so from this very sort of innocuous seeming condition on a type T, or any one of those equivalent ones in the proposition, you get that T must be an infinite loop space. And infinite loop spaces aren't so easy to come by, so it's kind of surprising to me. A corollary of things, not really of this theorem, but of things on the previous slides, are that if you start with KGN, which is central, when you form B out 1 of that, you get a delooping, and the unique delooping is a KGN plus 1. So this gives a model for KGN plus 1. And on this model, we have an explicit formula for the H-space structure. We do this thing where we flip the band and take the path type. So one of the whole morals or themes of this talk will be that we're going to be taking certain models for Eilenberg-Mac Lane spaces. And on these models, we're going to be able to give very concrete descriptions of a number of operations. Okay. This is the first example of that. Now, you may know that KG n plus 1s represent the n plus first cohomology group of a type. You take the maps into the KG n plus 1 and you zero truncate it, so homotopy classes of maps. And the H-space structure represents the addition in the cohomology. So we have our tensor operation being an explicit formula for how to compute the addition. Now here's just a little aside that we're not going to need, but it just sort of emphasizes how surprising some of this is. So if I start with a simply connected pointed type, and its loop space has the property that the pointed self-maps form a set, then it follows that X is central and therefore is an infinite loop space. So the interesting thing here is I'm only putting a condition on the loop space of X. I mean, besides X being simply connected. And how does this argument go? Well, the way we do it is we first prove that loops X is central. And since X is simply connected, loops X will be connected. Loop spaces are always H spaces. And if the pointed self-maps are a set, then it's central. Now, X is a delooping of loops X, but deloopings are unique. So X must be B out 1 of loops X. And so then, by this result, it must be central. It's a slightly indirect argument, but we see that if the loop space of X is central, then X must be central because it must be B out 1 of that loop space. We don't know the converse. I'm going to mention that in a moment. So this whole slide is a bit of an aside just because there's a lot of puzzles about central types, and I thought I'd mention some of them. So, here's another example of a central type. It's easy to check that RP infinity cross CP infinity is central. But RP infinity cross KZ mod 2, 2. So I add the mod 2 here. That one's not central. And in fact, we know exactly which products of Eilenberg-Mac Lane spaces are central and which are not. It's a little bit hard to explain, so I didn't want to get into it. But there's a lot we don't know. So here's 3 questions. Is it true that every central type is a product of Eilenberg-Mac Lane spaces, like all the examples I've given so far, either a single Eilenberg-Mac Lane space or a product with 2 factors, and we have examples with more factors. We don't know if every central type is a product or if there's just some other completely different central types. Open question. We know that if loops T is central, then T is central. But what about the reverse? So if T is central, is loops T central? Well, it needs to be connected. So let's take the base point component of loops T. That's the natural guess. Don't know if that's true. And we also don't know that if T is central, are its truncation central. So I'd love to hear ideas at the end if you have them, because these are questions that we've been puzzled by for quite some time. Okay, so that was our detour on central types. And now we're going to move into the second paper, the one that's not quite available yet, but will be available soon. And I'm going to talk about cup products next. So the cup product is an operation on cohomology that makes it into a graded ring. I'm going to talk about it for the integers, but everything I'll do works for any ring coefficients. I'll just use the integers for simplicity. So the cup product will take a cohomology class in degree n, combined with one in degree m, and give you one in degree n plus m. And I've written group as a subscript here to say that these are going to be group homomorphisms. So on the inside, we have the type of group homomorphisms, which is a group itself, since this is abelian. And then I have a group homomorphism from Hn to that type of group homomorphisms. That expresses the fact that this operation is bilinear, which is one part of being a ring structure. So this was first constructed by Guillaume Brunerie in his thesis for the integers, and then it was extended to other rings by several groups of people recently that I've written down here. And we're going to give a new approach, which gives, again, a concrete formula for the cup product. Okay, so there's a little trick. This isn't really necessary for what I want to say, but there's a little trick that simplifies things. So in general, when you want to give a map between representable functors, you can give a map on the representing objects. So if I have a map from KZN to KZM, it induces a natural transformation on the cohomology functors. But I'd like to get group homomorphisms. So if the map I have is a loop map, if it's loops of a pointed map on the deloopings, then the transformation I get is automatically additive. And so what I mean here, of course, when I take the loops of G, I'll get an omega in front of these, and then I use the equivalences to these two types on either side of that loops G. So if I wanted to apply this observation here, first of all, for the inner set of group homomorphisms, right here, what I'll want is a map from a KZM plus 1, increasing the superscript by 1, to a KZN plus M plus 1. So this type will give me group homomorphisms. But now I want group homomorphisms into that type considered as a group. So I need to deloop this pointed mapping type. So we need to deloop that. So the way I do that is by delooping the codomain. I put a +2 here. Because as I mentioned before, the loop space of this is computed by passing the loops into the codomain, which gets me to this. So altogether, to get this bilinear map, I should produce a bipointed map of this form, where I've increased these by 1 and I've increased here by 2. Now, if you look at it and you treat this as something to do for all n and m, I haven't really done anything. I've just replaced the n and the m by their successors. And that's I end up with 2 here because there's 2 successors. So I've got the same goal, but there's 2 reasons why this is an advantage. One is that it relieves me from dealing with the 0 case. And the 0 case is special because when you take maps between Eilenberg-Mac Lane spaces of the same degree and you loop, you get an equivalence on pointed maps, except in the bottom degree where you have to take group homomorphisms for your equivalence to be correct. And this avoids having to treat the bottom case specially. The other reason is that once we've got these maps and then we go backwards along this construction, we automatically get group homomorphisms without having to check that separately. So it's just a little trick that we use. Okay, so that gives us a goal here. We'd like to define this bipointed map for all n and m. So again, the trick will be to use a good choice of these Eilenberg-Mac Lane spaces. So what I do, first I'm going to use K1 for a KZ1, and I'll use any KZ1. I don't do anything special for that choice. But then from then on, I keep applying B01 to the previous one. So I get these iterated B01 constructions. If you're worried about universes, you can show that these are essentially small at each stage. So you can translate down to an equivalent small type. Okay, so I'm going to use this particular construction. Now, that means when n or m is 0, I'll be involving this k1 that I don't have any special control over. So in those cases, I use one of the other methods to produce my cut product map here. It's in the inductive steps where I can do something that isn't even inductive. I just can give a formula. So if n and m are both at least 1, then in that case, I'm trying to look at a kz n plus 1 where n is at least 1, which means I know it's of the form b01 of a kn. And same for here, and same for here. The 2 has been replaced by a 1. So I'm supposed to define an operation of this type. So I take a kn-oriented type and a km-oriented type, and I form their join. So the join is the type you get by taking the disjoint union of x and y. And then for each pair, where I take a point in x and a point in y, I put a path between those points. Joins are going to come up again later, so I'll say a bit more then. I take that join, I truncate it to the truncation level of this Eilenberg-Mac Lane type, and then I put in an orientation. I said it requires a bit of work. It's not that it really requires work. It's just a bit more than I want to say in a talk. You need a connectivity lemma about joins in order to get the orientation here. So you can show that that this type is merely equivalent to a kn plus m plus 1, and that you can get a homotopy class of equivalences. So it's a very concrete construction. It's basically you join the types you have, truncate them, and then you have to put an orientation on that. Now we need to know that this map is bipointed. And that follows from a fact that's worth mentioning because we're going to use it again. If I have an oriented type where t is central, and I have a point in that oriented type, then I get an equivalence or a path from my oriented type to the base point. So pointed oriented types are trivial. We think of these oriented types as torsors for this type. So this is analogous to the fact that a pointed torsor is canonically equivalent to the standard torsor. So to check the pointedness, I need to take the base point of either one of these. So for example, the base point of b01 kn is kn with its trivial orientation. And then I join them, but that has a point since kn has a point. So therefore, when I do this operation, the join of those two the truncation of that join will still have a point, and it'll be oriented, so it'll be trivial. It'll be equal to the base point. And same for the other factor. Okay, and then the claim is that those maps do give the cut product, at least up to a psi. So this is a part of the argument where we've written down a fairly complicated diagram in order to compare these. We're comparing with the approach David Vard has written down, where he defines these by inductive delooping. And so we need to show that all of these maps deloop to each other, which leads to a fairly complicated diagram. And there's a pointed homotopy needed at one spot. And we can show that there is a homotopy, and the pointedness of that exactly is the choice of a sign. So it certainly will be pointed up to a sign choice that we could put in at some point. And so we, at this point, can show it's the cut product up to a sign. Okay, so this is an example. This is our second example of how, by choosing appropriate models for Eilenberg-Mac Lane spaces, we can get a concrete description of the operation. In this case, it's the multiplication in cohomology that we get a description of. Okay, so now let me move back to bundles. And another sort of operation that involves cohomology is the Euler class. So first I'll describe the universal Euler class. So this takes an oriented n sphere and produces an oriented Eilenberg-Mac Lane space. And all it does is it takes your oriented n sphere and it n truncates it. So we know that the n truncation of the standard n sphere is a model for KZN. In fact, in this part, you could choose this as the definition, and that's one of the points is we encourage sort of flexibility in your choice of Eilenberg-Mac Lane objects. So we could make this our definition, but in any case, there's an equivalence. And so since our x has a 0 truncated equivalence to Sn, this truncation will have a 0 truncated equivalence to KZN. So it'll be oriented. And then in general, if I give you an oriented sphere bundle, I just post-compose with this universal Euler class. And then I take the homotopy class of that, which gives me something in the 0 truncation. But remember, this is a model for KZN plus 1. So I get something in the n plus first cohomology of the base with coefficients in the integers. And again, it's very concrete. You take your sphere and you truncate it. So the Euler class just converts a sphere bundle to a KZN bundle by truncating the fibers. So how do we know that this is the Euler class? So throughout the rest of the talk, I'll be telling you some properties about the Euler class and how it relates to the Thom class and how it relates to the tangent bundle of the sphere that show that it has all the properties we expect the Euler class to have. So let's start with the relationship to sections of a bundle. So classically, the Euler class is the first obstruction to the existence of a nowhere zero section of a vector bundle. So since we're taking our sphere bundles to model the non-zero vectors in a vector bundle, for us, nowhere zero section just means section. So the Euler class should be related to whether or not a sphere bundle has a section. And the first result in one direction says that if you have an oriented sphere bundle, and if it merely has a section, then the Euler class is 0 in cohomology. So let me sketch that. So this is an equality in a set, the cohomology set. So it's a proposition. So we can assume that P actually has a section. So this section here. Then when I compose P with E, remember that by definition just truncates the fibers. The underlying type of that composite is the truncation of the fibers. That means I can take the image of my section in P of B under the truncation map. So I get a point. And remember, this is a KZN oriented type. So here we have an element of a KZN oriented type, which means it's trivial. Remember, a pointed torsor is trivial. A pointed oriented type is trivial. So this type is pointed and it's in B01 KZN, so it's equal to the base point. So we've shown that this composite function, E composed with P, is homotopic to the constant function, which is what represents the 0 class in cohomology. There's a partial converse. So if we have a bundle whose base is an n plus 1 sphere, then if the Euler class is 0, then P merely has a section. And this is exactly what you would expect from the classical theory. We wouldn't expect a result like this to be true for any base, because this is the first obstruction. And the first place an obstruction arises in the classical theory is when you reach the n plus 1 skeleton of a CW structure or some other cellular structure on your base. So it's when you get to the n plus 1 spheres that build up your base that the Euler class will tell you whether you can extend that far. So in the case where your base is an n plus 1 sphere, it's a perfect invariant of whether you have a section or not. I won't go through the argument here. The proof's a little bit longer than this one. But these are exactly what you'd expect classically, so that's a good sign. Here's another thing that's true classically that we can also prove. So in the classical story, you can take the direct sum of two vector bundles, the fiber-wise direct sum, and the unit sphere bundle in a direct sum is the join of the spheres. So we see this join arising again. And you can visualize this, for example, if you take a two-plane and a line in 3 space, and you take the unit sphere in the plane and the unit sphere in the line. The way you get the unit sphere in the ambient space is by connecting all the points on the circle to the 2 points in the line. So that's how the join works. So for us, we can model the direct sum of vector bundles by taking the fiber-wise join of our sphere bundles. So if we have mere spheres, we can join them, and you end up with a sphere of dimension n plus m plus 1. That's how the dimensions work. And it passes to oriented spheres. If you take 2 oriented spheres and join them, you get an oriented sphere of that dimension. And then the Whitney sum formula says that if I start with 2 oriented spheres, so I'm stating it in the universal case, and we join those 2, and then take the Euler class. That's the same as the Euler classes, and then I do my cup product operation. So this is, I've stated in the universal case, but it's true then for any 2 sphere bundles over the same base. I can do the fiber-wise join and post-compose with the Euler class, or post-compose each with the Euler class and then do the cup product in cohomology. And the proof, it's almost definitionally true. The way the Euler class works, and in this series, I'm not writing the orientations everywhere, so you do have to check that. But here, the Euler class of the join is the n plus m plus 1 truncation of the join. So the join operation on fibers takes the join of the types, and then I truncate it to do the Euler class. And then that same lemma that let us do the orientation on the Euler class also tells us that I can insert n truncations and m truncations here without changing things up to n plus m plus 1 equivalents. So again, there's a lemma about connectivity of maps between joins here. But then by definition, these inner things are the Euler classes. And then by definition, this is how we defined our cup product operation, by doing the join and truncating. So all the work is really in showing that this operation does model the cup product. That's where the hard part is. And then you get the Whitney sum formula sort of landing in your lap. Okay. Now let's move on to another invariant of bundles. The Euler class will appear again in a couple more slides. So first I'm going to give a proof of the Thom isomorphism. I'm going to do this in a way that's a bit slicker than what's appeared before. So this was first, again, proved by Guillaume in his thesis. But here's a proof that uses the ideas that we've been talking about, and it'll fit on this slide. So if I have an oriented sphere bundle, in fact, I don't need the orientation for this construction, but I will at some points below. I can take the total space and the first projection, and I can take the co-fiber of this map. So that's the push out of that map along with the map to the unit type. Take the push out, and by definition, I call that the Thom space of the bundle. It's got a point by including there, and it's got what I'll call the 0 section, this inclusion here. And this is related to what Emily was asking about. It's not exactly the fiber-wise join, but we'll see in a moment how close it is. Or sorry, the fiber-wise suspension, but we'll see how close it is. Okay, so then the theorem is that for all I bigger than 0, and I is independent of the bundle dimension, unpointed maps from the base to KZI are equivalent to pointed maps from this Thom space to KZI plus n plus 1. So the bundle dimension shows up as a shift here. And then if you take homotopy classes, you get the cohomology of B here, and you get the reduced cohomology of the Thom space here. So you get this equivalence with a shift between the cohomology of B and the cohomology of the Thom space. And the slick argument that I'll give is we'll start with the right-hand side. Well, first of all, the second one follows from the first, so I'm only going to write down the first. I'm going to start with the right-hand side. And here's where I'm going to use that this is almost the fiber-wise suspension. You see, for any particular point here, I've got P of B is the fiber above it. So when I do this push out, I'm going to get the suspension of P of B. But when I do that, the south poles will vary to all the points of B, but the north poles will all be the same point. So I need to further identify all those north poles to one point. But if I'm looking at pointed maps out of these suspensions where I point this at the north pole, then that automatically handles that. All of these pointed maps, one for each B, all must send the north pole to the same point here. So that pointedness automatically takes into account that to get the Thom space, I should be also identifying all the north poles here. So maps from the Thom space to any pointed type are the same as, so pointed maps from the Thom space to any pointed type are the same as a family of pointed maps from the suspensions of the fiber. But now my claim is that the family in parentheses here is a trivial family, equivalent to KZI. And here's where we use orientations. So P of B is an oriented n sphere. So its suspension is an oriented n+1 sphere. The type of pointed maps from an n+1 sphere into type gives me the n+1st loop space. So that gives me a mere KZI for this mapping type. But because I have an orientation of this domain sphere, that gives me an orientation of the whole thing to KZI. And it's also pointed because I can take the constant map here. So I get an oriented pointed type it's a KZI oriented type that's pointed, so it's equivalent to KZI. That actually works when I is bigger than 0. But the fact that we're really using here is simply that the set of pointed self-equivalences is a set, because we have a set truncated equivalence from this type to KZI, but the type of those equivalences is a set, so I can remove the set truncation and get an actual equivalence. So that lets me trivialize this pi type and see that it's the same as just the unpointed types maps here. It's unpointed because this pi is unpointed. Right, so that gives us the Thom isomorphism. All right. Now, usually the Thom isomorphism is discussed using the Thom class, and we also have that. So the Thom isomorphism, I've repeated it right here. And if we take the case when I is 0, it's telling us that the maps from B to the integers is equivalent to the maps from the Thom space to KZ n+1. So I'm going to define the Thom class of P to be the element on the right-hand side that's the image of the constant map at 1 here. There's also a more sort of concrete thing I can say, but for this talk, I'm going to say it that way. And then you can show that up to sign, that Thom isomorphism is given by taking the cut product with the Thom class in a certain sense. You have to change domains appropriately, but that's what's going on here. So this is often how it's defined, and this approach, you get the equivalence easy, and then you can define the Thom class from the equivalence. But here's the thing that's more non-trivial and more important for the talk. This Thom class is a class in the n+1st cohomology, but it's in the cohomology of the Thom space. And remember, I have this 0 section from the base to the Thom space, so I can pull back that Thom class by precomposing down to the base. And now it has the same type as the Euler class. And the claim is that it is the Euler class, which is, again, a classical property that relates the two, that shows that we're doing something right here. And the way we prove that is by giving another definition of the Thom class. It's a definition that is a bit awkward. It's not sort of obvious that it's correct, but it is obvious that it restricts to the Euler class, basically by definition. And then we have to do a little bit of work to show that that alternate definition agrees with the one that's been defined up here, which we can do. Okay, so that shows another fact relating these classes. Okay, I've got just a few more slides and a few more minutes, so let me go through here. So let's get to the tangent bundles of spheres. So we constructed for every n, an Sn bundle on the n+1 sphere that we call the tangent bundle. So again, we think of it as the unit sphere bundle or the non-zero vector bundle of the tangent bundle. And along the way, we also give these equivalences that show that when I take the direct sum of this bundle with a trivial line bundle, I get a trivial bundle one dimension higher. And geometrically, this is exactly what happens for the tangent bundle to the spheres, because they can be embedded in ambient Euclidean space. And you can see this very directly. We do this, partly because it's partly a verification that we have the right bundle, but we also need it as an inductive hypothesis to do the construction. We actually prove something more general. For certain types E, we show that their join powers have things that we call tangent bundles. When you take E to be Boole, the n+2-fold join power of Boole gives me Sn+1, and so we recover these. But one of the reasons we do this more generally is it works for any two-element type, not just Boole. That lets us get tangent bundles for RPNs, real projective spaces. And it works when E is a circle. And it doesn't simply reproduce the tangent bundles of the even spheres in that case. It gives us tangent bundles for complex projective spaces. Okay. Now, I won't say any more about this because David Jasmyers gave a beautiful talk with lots of nice pictures in the fall that talks exactly about these bundles. So I'll let you watch his talk. But here's what we can show. This is the Harry-Ball theorem. It says that the tangent bundle of the n+1 sphere has a section if and only if the dimension of the base sphere is odd. And I'm going to sketch two arguments. The first goes like this. First of all, on the odd spheres, we have to construct explicit sections. And this is a little bit tricky. Classically, there's a simple formula, but in this homotopy invariant world, we have to do a bit more work, but we can write down explicit sections. To go the other direction, we first prove a result for every n, even or odd, that shows that if you have a section, then you can produce a homotopy which shows that the identity map on the n+1 sphere is homotopic to the antipodal map. This is exactly what happens in the classical proof of the Harry-Ball theorem. So here, minus x is a natural antipodal map that you can define on spheres. And then you can use degree theory to show that the antipodal map on Sn+1 has degree -1 to the n+2. The identity map has degree 1. So this is a contradiction when n+1 is even. So that's one argument. Another argument uses Euler classes. You can actually calculate that the Euler class of this tangent bundle is 1 plus -1 to the n+1 up to an overall sign. And remember that the Euler class is the obstruction to finding sections, and it's a perfect obstruction when the base is a n+1 sphere. So there will be a section if and only if this Euler class vanishes, and it vanishes exactly when n+1 is odd. So this proof is actually better in some ways because it tells us more. It doesn't just tell us that the tangent bundle fails to have a section. It tells us the way in which it fails. It fails in a degree 2 way, not a degree 1 way or a different degree. And that's exactly what happens classically for the tangent bundle to the spheres, to the even spheres. They have Euler class 2. And just as an example, the Hopf vibration over S2, it's also a circle bundle, but it would have Euler class 1, not 2. So it would fail to have sections in a different way that would let you distinguish those two bundles. Okay, so just one final slide to display. I want to summarize all the things we used BIOT1 for. So by definition, it's the classifying type for oriented bundles. But using it, we could define addition and cohomology using that tensor operation. We could define multiplication and cohomology using join. We could define the Euler class using n truncation, and then prove the Whitney sum formula using the multiplication we defined in cohomology. We could prove the Thom isomorphism, and we could define the Thom class and then prove the restriction to the Euler class. And then we could use the Euler class to prove the Harry-Ball theorem. So I think it's kind of nice that this same construction appears in all these different ways. And then I'll just repeat the references. I'll quickly mention that some parts are pushed to the COC library. A lot of the material on central types is still in this public repository. And almost everything else I talked about is formalized using the COC library, but it's currently not yet public. I just need to polish up a little bit more before I'm comfortable releasing it, but I'll be doing that as soon as I can. Thank you very much.
All right, let's thank Dan with our traditional silent applause. Great, and now we have some time for questions and discussion. So please feel free to unmute whenever you want to start. I guess I'll ask something. So at the very end in the proof of the Harry-Ball theorem, you described sections failing to exist in a sort of degree 2 way.
Mm-hmm.
I wasn't sure entirely what you meant by that.
Yeah, so the way we actually compute this this Euler class involves showing that there's a method for computing it. And the method for computing it, at least for example, for a suspension like this, is you start by choosing a section over the North Pole, which you can do because the fibers are inhabited. And then you can extend that section across the equator. And the question is, when you extend down to the South Pole, do the extensions agree or not? And at the South Pole, the extensions are parameterized by the equator. So you end up with a map from the equator, which is Sn in this case, to the fiber over the South Pole, which is also Sn. And in the case of the two-sphere, you end up with a map from the circle, the usual equator, to the tangents, the unit tangent vectors at the South Pole, which is a circle. And you can geometrically see that when you try to do that extension, you wrap around 2 times at the South Pole. And there's no way to fix that. That 2 is the 2 that the Euler class is showing. And we actually show that that method does correctly compute the Euler class. I mean, there's some sign choices you have to make because you have to orient things. But if you do the same thing for the Hopf vibration and try to extend a section from the North Pole to the South Pole, it'll wrap around once at the end. So that distinguishes those 2 bundles, whereas the binary question of just do they have a section or not doesn't distinguish those 2.
Great, and maybe I'll just ask a second question while I'm here. So you mentioned earlier that you know sort of precisely that the Euler class detects sections in the case where the base is a sphere. But
Yeah,
not
that's right.
You have a one-way result in general, but sort of a partial converse. I mean, I'm wondering if you have any other cases of the sort of converse result and whether there are sort of, I don't know, generalized Harry-Ball theorems or something like that.
So we haven't tried to do this for a general cell complex with cells up to dimension n+1. It should work. We just haven't thought about how to do that. And in terms of a generalized Harry-Ball theorem. I think, the answer as to whether a tangent bundle has a non-zero section, it's a very rich story, and it depends on the base space. There isn't some simple criterion that will tell you in general. There's some criteria, like if the base space is an H space, then its tangent space should have a section. And that handles S1 and S3 in this case, but not the other ones, at least not from what we know so far in HOT. But yeah, I don't think there's a simple answer to that. I see a couple of questions in the chat too. So Ali asked, why is B aught 1 essentially small? But really the point is that B aught is already essentially small. And that's by Egbert-Reich's join construction. So it's a component of the universe. So it has the same identity types as the universe, but it's got a surjection from a single point because it's connected. So it's locally small and has a surjection from a small type, so it's small. And B aught 1 just adds an extra small condition to that, so it remains small. Right, and then Martine is asking about the one-point compactification. So the Thom space construction here is really like a global one-point compactification, where I'm adding a single point at infinity to all of these spherical fibers. And the point I was making when I was describing this equivalence, which in our paper is spelled out in a lot more detail, is that you can do that in two steps. You can first do a fiber-wise one-point compactification, and then you can take all those new points, which are parameterized by B, and collapse out that copy of B as a second step. So the fiber-wise one-point compactification of these spheres is their suspension, and then you have to do a further construction to get rid of those points. But luckily, when we're dealing with pointed maps, that kind of just handles itself perfectly. So we end up being able to talk about maps out of the fiber-wise suspension being equivalent to maps out of the Thom space. I don't know if that exactly answers it, but feel free to ask for more. I see some nodding, so good.
Thank you. Makes sense. Anyway, your talk was very nice and clear.
Thank you. I know I packed a lot in, but feel free to ask about any part.
Yeah, you did pack a lot of things. So can you comment on a philosophical point about this? So it's amazing how much this synthetic approach can do. Do you have a feeling of why this works so well?
That's a good question. There's this interesting dichotomy, I feel, where some sorts of problems just fit very well with HOT, with this synthetic approach, and in some ways are cleaner. You get rid of distractions that point set topology might put in your way, and you get results like, I think, this Thom isomorphism. I'd never really understood it, and now I sort of just see why it's true, and it's because we think of these mapping types and dependent families of function spaces that you wouldn't really write down in classical homotopy theory.
So you're saying that not only it is possible to do it synthetically, but you think it gives a better understanding?
Well, that was the first half of what I was saying. There's this dichotomy where sometimes things actually turn out to be easier, clearer in some ways, because we use things like dependent types and universes. But then there are other constructions where it seems very either tedious or even maybe impossible to prove some things that are elementary. So, you know, we get a mix. We get some benefits and some things that make it harder.
Mhm.
Can I ask a follow-up on that?
Yes, go ahead.
Yeah, I mean, this is maybe more philosophical, but when things get harder or impossible, what's sort of missing from hot that makes that the case?
Well, it's usually some sort of strict equality. You know, if we try to bring in things like geometric realizations and, you know, singular simplicial sets, things like that use strict equality, or they need a lot of coherence that we don't know how to do. So in classical topology, you can get away with encoding a huge amount of coherence by just saying you have strict equalities.
Yeah.
And because we can't do that, we're often stuck, just unable to deal with some kind of construction.
The usual problems.
Mm-hmm. I see Ali asked some more questions. I don't exactly understand. So I'm sorry, Ali, because I just saw this now and I don't know what the word "this" exactly means about. And I know your mic doesn't work, right? So, okay, so Ali chatted, never mind. So we can talk later if you want. Oh, my battery is just about to die. I think we better wrap it up.
Okay, I will stop the recording after we thank Dan one last time and take the final thing offline. So real quick, one more round of silent applause. And then an important announcement. So we have one more hottest talk this spring, but it's in 3 weeks, not 2. So on May the 2nd, I believe, the first Tuesday in May, we'll be back for our final talk of the term. Great, see you all then.